Okay, now I'm going to show you how to calculate allele and genotype frequencies. So remember, our allele frequencies are P and Q, and our genotype frequencies are P squared, 2PQ, and Q squared. So we're going to do an example with blood group gene, alleles M and N. And this exhibits codominance. So the heterozygotes have a distinct phenotype as well. So say that we have a sample size, I'll use little n for population size since big N is already an allele. We've got 200 people. And 114 have type M blood. That means they're MM heterozygotes. There are 76 homozygotes. And then 10 people have type N blood. They are NN homozygotes. And so P would be the frequency of the M allele. And that is given by twice the number of MM homozygotes plus the number of heterozygotes over twice the population size. So we use a 2 there because everybody who's type M blood has 2 M alleles, and then also we use a 2 down there because everybody is a diploid, and again, we're calculating allele frequencies here. So plugging numbers in then, 2 times 114 plus 76 over 2 times 200 yield 304 400, which is 0.76. So the frequency of our M allele is 0.76. And we could do that same thing for the N allele, or the faster way and more efficient way is remember that P and Q equal 1. So Q, which is the frequency of the N allele here, will be 1 minus P, or 1 minus 0.76. And so therefore Q equals 0.24. 76 from subtracted from 1 is 24. So those are our two allele frequencies, 0.76 and 0.24. Now let's calculate some genotype frequencies. We'll have to erase the board, or at least some of the board over here. So P squared, frequency in this instance of the MM genotype, and that's merely 14 200, which equals 0.57. 2PQ, frequency of the heterozygotes, those people with MN blood type, and that's going to be 76 over 200, 38. And then, as you figured by now, Q equals the frequency of NN, and that's going to be 10 over 200. And people with type N blood over 200 in the data set, and that gives us 0.05. And then to check ourselves, we add these 3 genotype frequencies together, and if we get 1, we know we've done it correctly. Now, if you're off by a tiny bit, like if it's 0.999 or 1.00 something, that's probably just due to rounding, and that's okay. But if it's 0.9 or 1.1 or something, then that's too much of a difference, and you probably made a mistake somewhere. Okay. Now, why don't we see if this population is in Hardy-Weinberg equilibrium or not? And we're going to do that with a chi-square test. So let me make some room using this. We'll use this same data. And chi-square goodness of fit test. And we'll have our phenotypes up here. Columns. So observed. There. 10, 6, 14, I believe, correct? Yes. So then the next thing is our expected proportions, which would be our genotype frequencies. So P squared for these guys, 2PQ for those guys, Q squared for those guys. And then next are observed proportions, which are what our genotype frequencies really are. And as we just calculated, they are 0.57 for type M blood people, 0.38 heterozygotes, 0.5 for the others, type N blood people, and that adds to 1. And next then is our calculating our expected numbers. So what we do here is multiply our genotype frequencies by the total. So 0.57 by the total gives us 116. I think it's okay to round these expected numbers too, but you don't have to. 72 there, and 12 there, and we make sure that they all add up to the correct amount in the data set. That's 200. And then back to familiar territory, observed minus expected. Let's see, -2 there, a 4, -2 there. And then remember, we square these. 4, 16, 4. And then we divide them by the expected numbers. So 4 divided by 116 is 0.03. 16 divided by 72, 0.22. And then 0.33 in the last column there, 4 divided by 12. And then you add these together. And our calculated value there is 0.58. Now we always use the same column. Remember the 0.05 column in the table, but our degrees of freedom is slightly different in these tests. It's not phenotypes -1, but it's the number of phenotypes minus our number of alleles So we have 3 phenotypes, right? M, Mn, and N, minus 2 alleles, right? M and N, and so that is 1. So, and then looking at the table, of course, you see our value is 3.841, which is larger than the value we calculated, so we failed to reject our null hypothesis. I forgot to define at the beginning, but you know what that is. So that tells us that this population is in Hardy-Weinberg equilibrium. Okay? And so that's how we do a chi-square test with population genetic data. Now, sometimes, though, we won't know the genotypes of all the individuals, we'll just know phenotypes. So let's look at a problem, and I'll show you how to solve it that way. But first, I need to make some room on the board. So here, there's a certain disease. And it's caused by a recessive allele. Little d. And so it occurs in 4% of the population. And we are asked to figure out, I guess I should say what percentage of the population are carriers of this disease. Okay, carriers, of course, would be heterozygotes, big D, little d. Okay, so when we're given a number in a problem like this, first thing we have to do to solve it is assume that the population is in Hardy-Weinberg equilibrium. And then this percentage, 4%, is really Q squared. So you know that Q squared is the frequency of the little d, or diseased people, if you will, and 4% is 0.04. So now we know that Q squared is 0.04, and from here we can solve the problem by Q equals the square root of 0.04. And so that comes out to be 0.2. So we have Q is equal to 0.2, and now P equals 1 minus 0.2, which equals 0.8. So now we have our 2 allele frequencies, and now all we have to do is calculate 2 more genotype frequencies. So then, since we're assuming Hardy-Weinberg equilibrium, P squared is the frequency of the big D homozygotes, and that is 0.8 squared, because 0.8 is P, and so that comes out to be 0.64, and then 2PQ, remember, is the frequency of big D, little d. That is 2 times 0.8 P times 0.2 Q, and that gives us 0.32. So the answer to our question, 32% are carriers. So it's a third of the population are carriers, but only 4% of the population have the disease. And so it's important that you realize then the distinction between these two ways of doing problems. Okay, here you're given one number, that one number is always going to be your Q squared. You can't take 0.96 and solve it that way, because in the normal people, you've got two genotypes. You've got big D and big D little d, so taking the square root of 0.96 in this case would be meaningless. So don't do that. Always make sure you're going after Q squared, the homozygous recessives. And that is all I have for this lecture.